Carly McAvoy. Yesterday I did a video up to number 14 and then realized that I hadn't had the camera on what I was thinking I was on, so I'm going to do these 11, 12, and 13 again. So based on a poll of 66% of internet users, based on a poll, 60% of internet users are more careful about personal information when using a public Wi-Fi hotspot. What is the probability that among 3 randomly selected internet users, at least one is more careful about personal information when using a public hotspot? How is the result affected by the addition of information that the survey subjects volunteered to respond? Let's answer that right now. When you get a voluntary response, it messes up your study. No matter how great your math is, your math cannot overcome a crappy sample. So that's it. This is our answer, but how do we get it? So when you're saying at least one, person is more careful, then it could be 1, but at least 1 means it also could be 2 or 3. You're going to look at 3 people and at least one of them are careful, maybe 2, maybe 3. So that's why it's such a high probability is, we think, yeah, at least one of them are going to be careful. And so you can use your calculator for that. What you're going to do is you're going to find out what's the probability that 0 people are careful. And then whatever that probability is, which turns out to be this number, subtract that from 1 because the people, the 1, 2, or 3 are the rest of that. Because in that sample space, it could be nobody was more careful, it could be 1, it could be 2, it could be 3. So if you find out what 0 is and subtract from 1, then it accounts for all the rest of them. So how am I going to do that? Should have had my calculator out. We're going to go to a binomial distribution here. And so I hope you can see the calculator. I'm going to do data, second function data, sorry. Actually turn it on. Second function data, and then go to the right one where it says distribution, and then go down until you see binomial PDF, CDF, PDF. Okay, and then hit enter. And then you want a single trial. You're just finding out what 0 is. So how many? So in this case, our number of trials is 3 because we're talking to 3 people. The probability of success is given in the problem as 66%. That's why 0.66. And then we want to know how many people are we going to find that actually are being more careful, and we choose that to be 0. We want to find out what 0 is and then take that away from 1. So then I hit go down to calculate and hit calculate, and that's how I got the 0.039304. That's the probability that if we talk to 3 people, none of them are more careful. It doesn't happen. Only 4% of the time would we expect to see that, because usually 66% of the time out of 3, we'd have 2 people being more careful when they're working in public. So I take that and I subtract the 0 probability, and then it shows me the 1, 2, and 3 right there. So that's number 11. Number 12. So the answers are showing because, I did this earlier and I'm not going to reprint it, so I'm just going to do it. That's okay. Number 12, the data represent the result for a test for a certain disease. Assume one individual from the group is randomly selected. Find the probability of getting someone who tests negative given that he or she has a disease. That's a conditional probability. They're testing negative, so that's the N on top. But we're given that they had the disease, yes. Yes, they have the disease. That's what I have there. But you could use other letters. That's just what I called it. Okay, so they're negative given that they, yes, have a disease. So if I go and add up all these columns and rows, I get 145, 155, and then this way 154, 146. When I write the probability, I'm interested in putting on the bottom this, which is the probability that the person has the disease. If the person actually has a disease, yes, that's 145. So that looks like 145 on the denominator. Then I'm asking the top, what's the probability that someone is negative? So here's the negative results right here. But we know for sure, we already said they have to be in the yes column. So there's 11 people that tested negative that are also in this yes column. So that's 11 over 145, which gives us the 0.076. Okay. Number 13, the table below displays the results. with the polygraph instrument, find the probability that a subject lied given that their negative test result, and compare this result with the probability of selecting a subject with a negative test result given that the subject lied. So you flip-flop them and you see, are those two things equal? So what I'm going to do is add up my negative test results here is 43 and the yes is 57. Because this is, did the subject actually lie? That's what we're interested in, that they actually lied. There was 57 of them. That they had negative test results, there were 43. Now on the bottom, first of all, is the negative test result. So I put the negative test result was 43. And then the probability that they lied, well, did they actually lie? Yes. But they have to be in the negative column because we said this is conditional on. They're definitely in the yes lied column and they have negative test results. So that's 12 over 43. And for the other way, we're saying find the probability they had negative test results given that the subject lied. Did the subject actually lie? Well, that's 57. That's where we get that in the denominator because that's what's in the denominator. The negative test result here, when it falls into the yes column, is 12. So it's 12 over 57. And so we have 0.211 compared to 0.279. So they're not the same. They do not compare. All right, so you can't just flip-flop those and expect to see the same result. Okay, let's go on to number 14. I have not done this one yet. I got to here yesterday. All right, so the accompanied table, it's down here, so I have to show it. It doesn't really matter if you see the answer ahead of time, but we'll cover it up just because that's my, I don't know, anal retentive attitude there. Okay, so the accompanying table displays results from the polygraph instruments. Find P, the subject told the truth given that they had a negative test result. So negative test results, if you add those across, 34 plus 9 is 43. So I know that I'm going to have a denominator of 43. That's what's on the bottom. That the subject told the truth and they're in this category. So I come back up here. Did the subject actually lie? No, they didn't lie. They told the truth. I have to find that in my first column, which my first what I looked at first, which was the negative test result. So they didn't lie and they were in the negative test result. That's 34. So I get 34 out of 43. All right, and 34 is 0.791. Did they ask us to go out 3 places? Yeah. All right, and now on the second one, find the probability of selecting a subject with a negative test result given that the subject told the truth. And so we flip-flop them again. So we have a subject told the truth on the bottom. Did they tell the truth? Here, that's 50 people. So that's our denominator. And then we want to know, of the people in this column, how many of them had negative test results? Well, negative test results were 34. And 34 divided by 50 is, did they put 0.60? Yeah. 0.680, because they asked for 3 decimal places. We just tack a 0 on there. All right, compare the two values. Are they equal? Well, nope. We just saw that. When you have two, when you flip-flop them, you do not get equal values. Okay, let's move on. Testing for a disease can be made more efficient by combining samples. If the samples from 3 people are combined and mixed, and the mixture tests negative, then all 3 samples are negative. On the other hand, 1 positive sample will always test positive, so no matter how many negative samples it is mixed with. Assuming the probability of a single sample testing positive is 0.02, find the probability of a positive result for 3 samples combined into 1 mixture. Is the probability low enough so that further testing of the individual samples is rarely necessary? What we're trying to find out here is, can we just do this, and then every once in a while, if we get a positive, we have to go back and test all of them individually. But we could just mostly get negative, so if we test a bunch and they all come out negative, then we wouldn't have to go back and test them individually. So that's kind of what we're looking for. Let's think of this as a binomial probability where we're going to deposit 3 samples. So let's say that n is 3. And then we want, it's a 20% chance, the probability of success. In this case, it'd be bad because you have the disease, but they're going to call that a success anyway. Or testing positive is 0.2. Find the probability of a positive result for 3 samples combined into 1 mixture. This is similar to the other one because if we have 1 sample in there, it's going to make a positive result. If we have 2 positive samples, it'll make a positive result. Or if it will have 3 positives, we'll have a positive result. So the only time we don't have a positive result is if we have 0 positives in the sample, right? So I want to do that. I want to find out, well, what's the chances that I'm going to get 0 positives. And then whatever I get, I'm going to say 1 minus the probability of getting 0, because if I take away the zeros, then I have all the other ones left. So that seems like a good strategy to me. I'm going to do this by doing second function data, go 1 to the right, and then go down to binomial PDF, and I'm going to do one single thing, which is the 0. I have 3 trials again, but my probability of success is 0.2. But I want 0 of those again. So what I get is the probability of 0 is 0.512. So I'm going to say 1 minus 0.512. And that's going to give me 1 minus 0.512, 0.488. So about half the time I'm going to get a positive, and about half the time I'm going to get a negative, right? It's just a little over half the time I'm going to get all negative results. Well, I don't think this is going to save them any money, because half the time they're going to have to go back and run the other tests. But the probability is not low, that's for sure. So further testing would be necessary. Further testing of the individual samples will not likely be a rarely this is what I would answer the D part, because the probability this is going to happen is not low. So since it's not low, you're going to have to do a lot of retesting anyway. But so I think it's D. All right. In horse racing, a trifecta is a bet that the first 3 finishers in a race are selected, and they are selected in correct order. So you say like horse number 8, horse number 2, horse number 1. They have to be in that order. You got the order right, then you win if that's what happens. Does a trifecta involve combinations or permutations? So the difference between these two is that a permutation, the order matters. And for permutations, order matter. Combinations, order doesn't matter. That's how that goes. So because the order of the race is, you have to get them in the right order, the order matters here, so it's a permutation. Because the order of the first 3 finishers does make a difference, the trifecta involves a permutation. That's all they wanted me to say there. So you have to know the difference between when there's order matters and when it doesn't. All right, a thief steals an ATM card and must randomly guess the correct 3-digit PIN code from a 9-key keypad. Repetition of digits is allowed. What is the probability of a correct guess on the first try? The number of possible codes is, okay, so there's 9-key keypad, which means we have, first of all, does the order matter? Because we have to know whether it's a combination or permutation based on what does the order matter. Well, 1, 2, 3 is different than 3, 2, 1. So yes, the order does matter because each number is different. So we have a permutation because the order matters, and we have 9 keys, and we're trying to guess a 3-digit code. So we put that into our calculator, and that's this button right here. You have to push it 3 times, but first of all we're going to put in the number of things we have. We have 9 different numbers to work with, so we put 9, and then we push it 3 times till you get NPR, and then we're going to select a 3-digit code and hit enter. Wait a second. Repetition of digits is allowed. Oh. Okay, so the first digit, okay. So the first digit we choose, we have, this is what I have to do because I didn't think about this. This changes it, right? The repetition of digits is allowed. If we were told we couldn't repeat, like it can't be 111 or it can't be 121 or whatever, then this would be what I want to do. But what they're actually saying here is that we can repeat. So what we want to do is choose 9. We're going to choose 1 for the first digit. We're going to multiply that and do that again. Now we're going to have 9. We're going to choose 1 randomly for the second digit. And then we have 9 and we want to choose 1 for the third digit. So each one of those, and since we're doing successive digits in a row, we want to multiply those. And of course 9 choose 1 is just 9 because there's 9 ways to choose one number. That's what that says. So if I do 9, choose 1, I find out that I get 9. So I have 9 times 9 times 9, and 9 to the third power is 729. So there's 729 different ways to pick 3 numbers, and then the probability that you'll get it on your first try is 1 out of 729 chances. So you can see how if you do a 4-digit code, which is what most of them do, then we have 9 to the 4th power. So there's 6,561 possibilities, and so the chance that somebody will guess your pin right is not very good unless you do something stupid like use your birth date or your son's birth date or your house number on your street or something like that where people can kind of guess. Those are common ones that people choose. So you want to try to pick a number that doesn't have any, that no one would be able to associate with you, something like that. I know a lot of people that are relatively young, but still, that use their lunch code from high school, middle school as their passwords. It's just interesting to me. They do that, like their initials with their lunch code. If I was trying to crack a code of somebody between the ages of 14 and 25, I would try that. I would find out their lunch code in high school, throw their initials on there, and see. Are you one of those people? I don't know. I've met at least 5 people who do that. So, just kind of interesting. All right, you know the names of the remaining 7 students in the spelling bee. What is the probability of randomly selecting an order and getting the order that is used in the spelling bee? So, I guess everybody's going to be in the spelling bee, right? So, you have 7 people. The order is going to matter because you're going to get the order, you're trying to get the order right. So you have 7, you're going to choose all 7. So we have 7, let's see if I got this right, and we're going to choose all 7. The answer is 5,040 different ways we can choose them. The chance that you're going to choose it correctly is 1 out of 5,040, right? So if you think about numbers in a lottery or something, I don't know how many numbers they have in the, like in pick lottery or the Powerball or something. But let's say there was 40 numbers. You don't really have to choose them in the correct order. So you just have to choose the 5 numbers and then a Powerball number too. So you have to choose 6 numbers, right? Let's say. And it's from numbers 1 through 40. So it's not, an order doesn't matter. So it'd be like this. You have to do the, there are 40 numbers, let's say. And let's say you just had to pick 5. I don't really know how that works. You have to pick separately a 1 Powerball. Anyways, I don't know. But let's just say 40 numbers, you got to pick 5. Order doesn't matter. How many different ways? There are 658,008 ways to pick those numbers. So you have 1 out of 658,008 chance of choosing that right combination if there were 40. Maybe there's more. I don't know. Anyways, probability the permutations order matters, combination order does not matter. Okay. All right. A fan of country music plans to make custom CDs with 14 of her 26 favorite songs. How many different combinations of 14 songs are possible? Is it practical to make every different CD for each possible combination? Well, she's going to take 26 of her songs. It doesn't say that the order matters, just going to put them on a CD. So we have a combination. We have 26 songs and we want to do 14 different songs on there. So it's 26, hit that twice, 14, and that gives us 9657700. 9,657,700 combinations. That's that answer. Is it practical? No, it's not practical to make a different CD for each combination because the number of possible combinations is very large. So we can't be doing that. No way. All right, number 20. A presidential candidate plans to begin her campaign by visiting the capitals in 4 of 50 states. What is the probability that she selects the route of 4 specific capitals? Is it practical to list all the different possible routes in order to select the best one? It doesn't say she has to go to one particular place first or second. So all we're doing is saying there's 50 different choices that she can make, and she's going to make 4 of them. So it's a 50, choose 4. And there's 230,300. That's this answer. Whoa, no there's not. How did I get so wrong? So is it not, if it's 4 specific capitals, is it a permutation? I like these ones that make you think a little bit. Why would it be a permutation? Does it say she has to go, and I guess because she said that she selects the route of 4 specific capitals. So I guess so. Going to Olympia, and then going to Jefferson City, and then going to Topeka, and then going to, oh my gosh, Montpelier, I guess would be different than flip-flopping those around. Okay, well, sorry about that. Live and learn. So that was a permutation, 50 choose 4. I think the key word that I kind of missed out on was that it was specific route, I guess. Okay, so no, it's not practical because the number of permutations is too large. Oh, it even says permutations if I would have read ahead. Well, I didn't. How many different ways can the letters of knitting be arranged? Whoops. How many ways can they be arranged? Doesn't have to spell a word. And we have 1, 2, 3, 4, 5, 6, 7, 8. And we want to arrange all 8 of them, right? We don't care about the order, right? So we can just, doesn't matter, different ways. So what if we had 8? Choose 8. 8. Boy, I'm really getting this goofy. All right, so let's see. How many different ways can they be arranged? Well, I think because we have duplicate letters, it changes things, right? So in the first letter, we can arrange the K into one of all these spots. But the N and the N, that doesn't change anything by putting those into different spots. So hang on a second. Okay, so I'm not going to try to use the permutation combination thing. We're going to use the fundamental counting rule. So what we're going to do is the number of ways that you can arrange knitting is this factorial key. I mean, I don't know if you watched the video on the explanation, but we talk about that. And so I have 1, 2, 3, 4, 5, 6, 7, 8 letters in knitting. So there's 8 factorial ways to combine those. And then what you do is you divide by the number of, when you have duplicate letters. So I have duplicate letters N, I have 2 N's, I have 2 I's, and I have 2 T's. So I have 3 sets of double letters. So I would do 2 factorial, 2 factorial, 2 factorial on the bottom. 2 because they're double. 2 letters, 2 letters, 2 letters. And 3 of them because there's 3 different double letters. And then I would put that into my calculator to solve it. So if I put the fraction bar in there, 8, and then hit this button once, factorial, and then I have 2 factorial, 2 factorial, 2 factorial. So that's what I want to simplify or solve, and that's 5040. All right, got thrown off there. Forgot about that dividing by the blah, blah, blah. All right, find the probability of winning a lottery with the following rule. Select 5 winning numbers from 1 to up to 25 in any order with no repeats. So the different ways we can do that, that's a combination. I know you probably don't trust me by now when I say that, but there's 25, there's no order matters, we can't repeat, so we're going to select 5. So we have 25, select 5, which is 53,130. Different ways. The probability of winning is 1 over that. 1 over 53,130, because you have 1 chance of getting that right out of 53 chances. All right. In a lottery game, the jackpot is won by selecting 4 different whole numbers from 1 through 45 and getting the same 4 numbers in any order that are later drawn. In the Pick 4 game, you win a straight bet by selecting 4 digits with repetition allowed, each one from 0 to 9, and getting the same 4 digits in the exact order that are later drawn. The Pick 4 game returns $5,000 for a winning $1 ticket. Complete parts A through C below. In the lottery game, the jackpot is won by selecting 4 different whole numbers from 1 through 45 and getting the same 4 numbers in any order that are later drawn. What is the probability of winning this jackpot? So there are 4 different numbers, so no repetitions. The order doesn't matter, so what do you think we need? We should use a combination here. We have 45 numbers and we have to pick 4 of them. And then the probability is going to be 1 over that number, whatever we get, because so that's 148,995, and the probability of winning that is 1 over that. There's that one. In the Pick 4 game, why'd they say it all and say it all again? I don't know. In the Pick 4 game, you win a straight bet by selecting 4 digits with repetition allowed, each one from 0 to 9, and getting the same 4 digits in exactly the order they are later drawn. What is the probability of winning this game? We have 4 digits, and each time, 0 to 9 is a total of 10 different things, right? So we have 10 different ones. We're going to draw 1 number, and we're going to do that 4 times. Because we have a chance of repetition, so we need to allow that. Every time we have 10, we're going to draw 1. So that changes things a little bit. So I'm going to do parentheses. I have 10, choose 1, and I'm going to take that to the 4th power. And that gives me 10,000. What is the probability that you would win? That you'd have 1 over 10,000. The Pick 4 game returns $5,000 for a winning $1 ticket. What should be returned if the lottery organization were to run this game for profit? What should be the return if the lottery game were to run this game for no profit? Oh, sorry. Well, if it was for no profit, then they should return the 10,000, because that's the odds. Like if there's 10,000 chances you should pick. So if they were going to do this without making a profit, there should be $10,000 returned. In other words, everybody should have a chance to buy in. They bought in for 10,000. if they were not making a profit, they would give 10,000 back, because basically you have one chance of winning and 10,000 chances of losing. So if you wanted to balance it out, they should be giving you $10,000. All right. Corporation must appoint a president, chief executive officer, and chief operating officer, and chief financial officer. It also must appoint a planning committee with 3 different members. There are 14 qualified candidates, and officers can also serve on the committee. Completes parts A through C below. How many different ways can the officers be appointed? Well, if you are a CEO, that's different than a COO and a CFO and so forth. So that's permutation, because the order matters on which you get chosen for. It's not just random. So there's 14 people, and you're going to choose president, chief executive officer, chief operating officer, and chief financial operator. So there's 4 different positions. All right, so 14, choose 4. 24,024 different ways. How many different ways can the committee be appointed? Well, that's a combination. You can already be on one of those things and still be on a committee, but being on a committee, you're not like, you're just on it. You're not like president or something. So all 4 people that get chosen, same deal. And that's 1,001. Heavens to bets. Did it already say? The officers can also serve on the committee. Oh, there's only going to be 3 members of the committee. I didn't read that very closely. I could see my answer was wrong, but I couldn't see. So you're going to pick 3 people for that. Well, that's 364. A lot fewer when you limit it. So 364. What is the probability of randomly selecting the committee members and getting the 3 youngest of the qualified candidates? So the 3 youngest are 3 out of 14, right? So when you're thinking about, think about how many different ways we can select the committee members. We already found that out in the last section, which was 364. So we want to say that that's our denominator, is 364 ways to pick that. How many ways can we pick the 3 youngest? Well, 1. If we pick 1, 2, and 3 youngest, we've done it. If we pick anything else out of those 364 ways, we haven't done it. So the probability of getting the 3 youngest is just 1 over 364. All right. Number 5, a combination lock uses 3 numbers between 1 and 50 with repetition, and they must be selected in a correct sequence. Which of the 5 counting rules is used to find that number? How many different combinations are possible? Is the name of combination lock appropriate? If not, what other name would be better? So, you know what's funny is that when you're talking about a combination lock, you're not really using a combination for that, because once we start allowing you to repeat numbers, it's not exactly a combination. So a permutation or combination don't allow numbers to be repeated if you're just going to use that. And the factorial rule is not it. So it's the fundamental counting rule that actually makes sense here. How many different combinations are possible? Because we can repeat, how many numbers are there? 3 numbers. So we have 50, choose 1, 3 times, right? So that's the fundamental counting rule. So we would have, you can just do that on your calculator. I've done those a few times. I feel confident to let you try that. Choose 1, but we're taking that to the 3rd power. So we get 125,000 on that. And then, I can't even see my calculator. Is the name of combination lock appropriate? Not really. The fundamental counting rule lock would be better, right? Because we just said that's what it was. So that would actually be a better name for it. All right, last one. Good, because I got to get moving out of here. How many newspapers carry a certain puzzle in which the reader must unscramble letters to form words? How many words can the letter refons be arranged? How many ways can it be arranged? Identify the correct unscrambling Then determine the probability of getting that result by randomly selecting one arrangement of the given letters. So I'm assuming that we have the opportunity to, we have to use all letters every time. There's no repetition in this, right? So we should just be able to take the 1, 2, 3, 4, 5, 6 factorial to do that, because there's 6 letters, and we don't have to divide by anything because none of the letters are being repeated. So 6 factorial, whoops, 6 factorial is 720. There's 720 ways to rearrange that. What's the correct unscrambling? Well, once they do that for you, like, duh, okay, it looks like frozen. What is the probability of coming up with that? Well, there's one chance of that out of 720, so it's 101 out of 720 chances to do that. Cool, that is homework 4B complete, and I will see you next time for 4A. Have a fantastic day.